We're going to discuss the boundary conditions that we can put on electric fields at interfaces between two different materials. These kinds of materials might be something as simple as from air to glass or from one dielectric to another. And we're going to see that you get different boundary conditions on D and on E. And essentially what we want to know is what will be conserved as we cross the interface. So first of all, we're going to consider boundary conditions on D. And to do this, we're going to consider one of Maxwell's equations. We're going to use the modified form of Gauss's law. Now, div D normally is equal to rho, the external charge density, but we're actually only going to consider the situation where div D is equal to 0, so there is no external charge density. A reminder that sometimes in textbooks they refer to free charge density, which I think is an enormously confusing piece of notation. So I will always refer to external charge density, in other words, charges which have been introduced from outside the system. So this is our standard Maxwell equation, but that's differential. There's not much use in that form. So we now consider an interface like this, and we're going to consider a volume. It's going to be a small cylinder which goes across the interface. We've got material 1 here and material 2 here, and we have a cross-sectional area of A and a height here of H. So we're going to use the divergence theorem and the integral form of Gauss's law in this form, so the integral div D dV, which we know is equal to 0, and then we will transform that via the divergence theorem in a standard approach to the integral form of Gauss's law, so that's the closed surface integral of d dot n dA, which is going to equal 0. So now let's just consider which surfaces we have to consider. There are 3 surfaces, so there's the top surface, there's the bottom surface, and I'm just going to put a sort of a dotted line in there to indicate where that bottom surface is, and then the edge of the cylinder. So we're going to ignore the edge because we will allow H to tend to 0. In other words, we're just going to enclose the interface in our integration volume, and therefore we can discard any contribution from that side wall of the cylinder. So now we only have the 2 top and bottom parts, and so what we would write would be D1. If we assume, actually, let's just draw in here a D field. I'll do it in green to make it clearer. So here is D2, and then we assume it's going to bend somehow at the interface. We'll study that later. And there's D1. And so now what we have is that D1 dotted with N multiplied by A. You could make that a dA or a ds or something else if you preferred. Minus D2 dotted with N times A must equal 0. We have the minus sign here, this minus sign, because at the interface, the normal to the interface on the 2 side is downwards, the normal on the 1 side is upwards. In fact, let me just introduce that. So that's N hat, and here we have N hat. So those have different signs, which is why we have different signs in this. And we've assumed that D is uniform over a small area, so rather than doing a surface integral, we've just pulled it outside and done the integral over the surface area, which gives us a factor of A here and here. And of course the inevitable consequence here is that D1 dotted with N is equal to D2 dotted with N. In other words, normal components are conserved. When there are no external charges. That's important just to remember that you have to have that caveat. And what this means is that lines of D are conserved, so field lines. And I will do another video talking about a small piece of material which has got a polarization, but what you can just recall to yourself is that lines of D will start and finish on external charges. So if there are no external charges at an interface, in other words, if it's either completely neutral or there are only polarization charges, then the lines of D will not appear or disappear. So the kind of thing we might see would be for a small piece of polarized material, which is going to behave a little bit like a dipole far away. Inside the material, lines of D must be conserved. So we would see, so if this is a piece of polarized material, I'll do a full discussion of this particular problem and a couple of others in another video, but you can see that what's happening here is that we're keeping the same lines of D here at top and bottom, whereas if we were considering the E field and there were charges of some kind of polarization charges at these interfaces, lines of charge could appear and disappear. So that's the D field. So now let's think about boundary conditions on E. And what we're going to do is we're going to use a different Maxwell equation, as you might expect. We're going to use curl E, and that would normally be the curl of E is equal to minus dB by dt. Now, at this point in the course, we're considering static fields, so we could argue that dB by dt is equal to 0, but actually we'll see that it doesn't matter what's on the right-hand side because it doesn't contribute. Now, this time, we're going to use Stokes' theorem, so we're going to draw our interface and we're going to put a little loop around the interface. We're going to label this, A, B, C, D, so we can go around the loop. And so we're going to say that the loop is bounding a surface S. So we could say the surface is S here. That's the surface whose normal is coming out of the page. We're going to say that we've got a height here, H, and a length here, L. Actually, that's not the best place to put that indication. Let's put that down here. Here's L. And then again, we're going to have an E field, which is going to come in here and then proceed on there. And here is E1. This is E2. So if we write down the surface integral of the curl of E, dotted with n dA, that's going to equal the surface integral of minus dB by dt, dotted with n dA. Again, what we're going to do is we're going to allow h to tend to 0. So this right-hand side just goes to 0 because the area will go to 0. The left-hand side we're not going to leave as a surface integral. We're going to use Stokes' theorem to transform this. And what we have now is that the closed loop integral of E dot dl is equal to 0, and that right-hand side is 0 because we've allowed the surface area to go to 0. Again, as we argued before, by shrinking h, we can discard the edges. So actually all we have is the following, is we have E1 dotted with AB minus E2 dotted with CD, and the minus sign comes there because again we're going around in a different direction. That's equal to 0. And so this tells us that E1 dot AB is equal to E2 dot CD. And so tangential components of E are conserved. And that, of course, means that at interfaces which have polarization charges, we can get new E field lines. And again, I'm not going to draw it because it gets a little bit more complicated, but in that example of a small piece of polarized material, you can see that, and I will have that as an example of calculations involving polarization as a separate video. I realise actually there's a sign, that there's a sign issue here. I'm actually going to change this to be a plus CD. And then what I'm going to say is that I'm going to define a line DL in that direction. And so this becomes E1 dotted with DL minus E2 dotted with DL is equal to 0. And then I'm going to change this line here to do the same. So that E1 dotted with DL is equal to E2 dotted with DL. I haven't pulled a quick one there, that's just making the signs a little bit clearer and the logic just a little bit clearer. It's really important to understand these boundary conditions because they can actually help you solve practical problems. It also means that you understand what's going on at the transition between materials. And so I urge you to work on this and understand it.